When you think about scientific discovery, it has always felt like this fundamentally human thing,
Absolutely. The driving force of civilization, really.
right? I mean, we trace our history through geniuses like Newton watching an apple fall, or Einstein completely reshaping how we see space and time. It's always been about human curiosity, human intuition.
It has been, yeah. But that entire tradition is being, well, completely disrupted. The sources we're diving into today talk about a massive shift.
You mean the emergence of these LLM-based artificial intelligence scientist systems?
Exactly. And we're not just talking about tools that help humans anymore. These systems are actually starting to take the lead. They're designing experiments, writing papers.
And some of those papers are getting accepted, right?
Okay.
I saw one was accepted at a workshop for ICLR 2025.
That's the one.
Wow.
And that signals a monumental shift in who or what is actually driving discovery.
So that's our mission for this deep dive. We need to answer the big question the sources are posing. How close are these AI scientists to, changing the world and completely reshaping the entire paradigm of scientific research?
Exactly. And to do that, to really measure the progress, we're going to use the four-level capability framework from the source material.
A kind of maturity roadmap for an AI scientist.
It's the perfect way to frame it. It defines every single step an AI needs to master to get to that point of fully autonomous discovery.
Okay, let's start with those foundational steps. This framework, it really just maps the traditional scientific life cycle that the AI is trying to automate.
It does. It starts with knowledge acquisition, then idea generation, verification, and all the way to evolution.
So level one, knowledge acquisition.
Right. This is the AI's ability to autonomously go out, retrieve, review, and actually comprehend the existing scientific literature. It's about building that foundational knowledge base.
We've definitely seen a lot of progress here.
Mhm.
I mean, before the LLM era, say pre-2020,
Mhm.
we had smaller models like Cyber.
And they were useful for things like text mining, but they were pretty limited in their deep understanding.
But the LLM era just supercharged this whole capability.
It really did. Now we have large models using techniques like RAG, retrieval augmented generation, and this is so important.
RAG is like giving the AI a library card to the most current information.
Right.
So it's not just relying on its old training data.
Exactly. Systems like DOR AI scientists use this for really complex literature searches.
So it sounds like a solved problem.
No.
But the sources, they point out a weak spot, even at this very first level.
They do, because even with ARG, the systems still lean a bit too heavily on simple keyword matching.
So they might pull a classic foundational paper from decades ago.
But miss the absolute cutting-edge paper published last week because the keywords aren't a perfect match. It shows a need for better contextual understanding. They know the history, but not always the latest breakthrough.
Okay, so the library card works, but it's still pulling the dusty 1980s edition sometimes. That brings us to level two, idea generation.
And this is where it gets really interesting. This is where the AI moves from just being a reviewer to an actual inventor.
Formulating innovative and crucially feasible scientific hypotheses. This is what makes it an AI scientist and not just an automation tool.
And the methods are getting incredibly sophisticated. They use things like chain of ideas prompting, which helps organize thoughts in a structured way to spark novelty,
We're even seeing multi-agent collaboration, like MooseChem in chemistry.
where different AI agents can propose and then critique each other's ideas, all in natural language. The sheer volume is just staggering. One system generated 4,000 seed ideas on a single topic.
No human team could ever match that volume. But like you said, volume isn't the same as quality.
It's not. And the quality of these ideas is judged on four things: novelty, feasibility, clarity, and excitement.
And this is where we get to a really surprising insight from the sources. There was a big human study.
A large-scale study, yeah.
Yeah.
And in a blind review, LLM-generated ideas were rated as statistically significantly more novel than ideas from human experts.
Let's just pause on that. More novel than human experts. Is this where we start delegating creativity to machines?
We might be. But there's a huge, huge catch here that brings it all back down to earth.
Okay, what's the catch?
While those AI ideas were more novel, they were also rated as being slightly less feasible.
There it is. Novelty is easy when you don't actually have to build it.
Exactly. And that gap, the one between an abstract, novel idea and the practical reality of making it work, that is the biggest roadblock on this whole roadmap.
And that transition from a cool idea to something you can actually test is where everything seems to break down. This brings us to level three, verification and falsification.
The ability to systematically design, implement, and analyze experiments to prove or disprove its own hypotheses. This is what closes the research loop.
And the scientific community values this above almost anything else.
We know that from the data. An analysis of ArcSift papers showed that papers with real substantive implementation details get way more citations.
Something like 25 citations on average versus just 10 for those without.
Right. The community rewards work you can actually execute and verify.
So what happens when we ask these AI systems to actually do the work? The sources suggest they just hit a brick wall.
The numbers are pretty brutal. Let's look at the benchmarks. On MLE Bench, which tests complex AI training workflows, OpenAI's top model only had a 16.9% success rate.
16%, so it fails more than 80% of the time.
Yes. And on another one, Paperbench, which is about replicating published papers, it only managed a 26% replication score.
Those are just fundamental failure rates. It's like AI is an incredible theorist who can write beautiful equations on a blackboard, but has no idea how to actually build the circuit.
That's a great way to put it. It shows this deep struggle to translate a concept into operational, correct code that actually runs.
So to deal with this rigor crisis, people are now developing AI reviewer systems.
Right. Systems like Deep Reviewer, which are designed to speed up peer review and assess quality. They're moving from simple scoring to multi-agent systems that can simulate a human review discussion.
But wait a minute. If the AI scientists are failing so badly at implementation, why are we rushing to have AI reviewers grade their work? Isn't that like letting them grade their own homework?
It raises some very serious questions about self-regulation, for sure, but the pressure for speed is intense. And what's really telling is when a rigorous human evaluation was done on 28 papers from 5 of the leading AI scientist systems.
Okay, and what did that find?
The results were catastrophic. The absolute best-performing AI system scored only 4.63 out of 10.
Barely a passing grade for the best of the best.
And the number one issue, the top defect, found in 100% of the papers they looked at.
Let me guess. Experimental weakness.
Experimental weakness, 100%. It's not a small gap, it's a chasm. No matter how novel their ideas are, they are universally failing at implementation.
And the other issues were just as bad. Methodological flaws in almost all of them, novelty concerns in nearly 90%. So even the novelty isn't always that novel.
Which means, if these systems can't verify their own work, they have to learn to get better. And that brings us to the final level, level 4, evolution.
The ability to learn from mistakes and get better over time. How does a machine even do that?
Well, one way is through dynamic planning. Systems like Xochi and AI Scientist V2 use tree search algorithms to map out different research directions and then learn which paths are more fruitful.
And then there's autonomous learning, right?
Yeah.
Self-reflection.
Exactly. A system like FunSearch does this. It has an LLM that generates code and an evaluator that tests it. The best performing code gets fed back into the prompt, creating this self-improving loop.
So this is designed specifically to get over those level 3 implementation failures.
That's the goal. But the sources point out a huge missing piece for the whole ecosystem to evolve.
A standardized scientist-to-scientist communication protocol, an SSCP.
Right. Without a common language, all these different AI agents and communities are basically working in silos. They can't collaborate effectively or share results seamlessly.
Even with all that, the entire structure is still built on LLMs, and they have their own deep-seated problems.
Absolutely. And those problems affect everything. The first one is obvious. Hallucination.
The AI just makes things up. Fake data, non-existent theories. In science, that's not just a bug. It undermines the very foundation of trust.
And then there's the problem of knowledge updating. Science moves so fast, but retraining these massive models is incredibly slow and expensive.
So they're always operating with a time lag. They're never truly at the state of the art.
Never. And related to that is catastrophic forgetting.
This is a wild one. When you train it on new stuff, it can actually lose its understanding of old foundational concepts.
Which is devastating for science. You need to connect historical insights to new information. If your AI learns quantum theory and then forgets classical mechanics, it can't make those cross-disciplinary breakthroughs.
This instability seems like a deal breaker for any kind of long-term coherent research.
It's a fundamental challenge of the underlying models.
So beyond the technical limits, what about the ethical and societal challenges here? These AIs have no ethical judgment.
And that's a major risk. They could accelerate the development of harmful technologies, say in cybersecurity, faster than we can create safeguards.
And there's the risk of research bias, too. The AI might just favor topics with lots of data, or high automation potential.
skewing the entire research landscape away from areas that are critical but maybe less data-rich.
Not to mention the risk of weakening our own skills.
Yeah.
If we over-rely on this, do we forget how to do the critical thinking ourselves?
It's a real danger, which is why the sources argue for immediate mandatory controls.
First on that list, no AI authorship.
Correct. Authorship comes with legal and ethical responsibility, which an AI cannot assume.
Plus a clear, mandatory labeling of all AI-generated content for transparency.
And a push for a global convention on ethical boundaries. We need rules of the road before we let these things drive.
Okay, so let's synthesize this whole deep dive. The AI scientist systems are brilliant theorists. They're great at acquiring knowledge and even generating ideas that are demonstrably novel.
But that creativity is completely bottlenecked by a universal, profound weakness in implementation and verification.
That 100% failure rate on experimental rigor really is the whole story. The gap between a great idea and rigorously executed science is everything.
It is. And level 4 evolution is all about trying to bridge that gap. The future will probably go down 2 tracks.
The first being the personalized AI scientist.
Right, a kind of co-pilot for individual researchers tailored to their workflow, maybe even their ethical boundaries, so it might auto-reject research into high-risk areas they want to avoid.
And the second track is the AI scientist for human society.
Big collaborative ecosystems of AIs focused on solving global challenges. Things like climate change, energy, or disease treatment.
What's really fascinating here is how this is all being framed as a systems engineering problem.
Exactly. It's about plugging together modules, an LLM, a Haragi system, a simulator. It's not trying to replicate the slow, messy, organic way that a human learns and discovers.
Which leaves us with a final provocative thought for you to take away. This modular, hyper-efficient path to discovery is very compelling. But what are the ethical and intellectual costs of pursuing it? How do we make sure that this approach enhances, rather than erodes, the critical thinking, the problem-solving skills, and maybe most importantly, the fundamental curiosity that's essential for the next generation of human scientists?